Introduction to Biosafety Cabinets, Essential Protection in the Microbiology Laboratory. A biosafety cabinet, or BSC, is a specialized laboratory workspace designed to safely handle materials contaminated with or potentially contaminated with pathogens. These specialized enclosures provide a controlled environment that minimizes the risk of exposure to hazardous biological materials. Biosafety cabinets are critical safety equipment in laboratories working with infectious agents. They are an essential component of laboratory biosafety programs. The design creates controlled airflow patterns that protect users by drawing air inward and away from the operator. Biosafety cabinets provide three types of protection. They protect personnel from exposure to hazardous materials, prevent environmental contamination, and in some cabinet classes, protect the product being handled from contamination. Biosafety cabinets are fundamental to safe microbiological practices and are required for work with infectious agents in research and diagnostic laboratories worldwide. Biosafety cabinets consist of several core components that work together to create a safe working environment. The HEPA filtration system is a critical component that removes 99.97% of particles that are zero point 0.3 microns or larger from the air. Controlled airflow mechanisms create invisible barriers that protect both the worker and the samples. The airflow patterns direct potentially contaminated air through the HEPA filters. The work surface is typically made of stainless steel to withstand harsh disinfectants and is designed for easy cleaning and decontamination. The viewing window or sash provides physical protection while allowing visibility. Maintaining the proper sash height is critical for correct airflow patterns. The control system monitors critical parameters like airflow velocity, filter integrity, and sash position, alerting users to potentially unsafe conditions. All these components work together as an integrated system. The control system monitors the airflow, which is directed by the cabinet design through the HEPA filters, creating a safe work environment on the work surface, all visible through the viewing window. Remember that all components must function properly to maintain biosafety. Regular certification and maintenance are essential to ensure the cabinet continues to provide protection. HEPA, or high-efficiency particulate air filters, are a critical component in all biosafety cabinets. HEPA filters capture 99.97% of particles that are 0.3 microns or larger in size, making them essential for laboratory safety. HEPA filters consist of a dense mat of randomly arranged fiberglass fibers. These interwoven fibers create a complex maze that particles must navigate through. HEPA filters utilize three primary mechanisms to capture particles: direct interception, inertial impaction, and diffusion. With direct interception, particles follow the airstream but are large enough to contact and stick to filter fibers as they pass by. With inertial impaction, particles are too heavy to follow the curving airflow around fibers. Their momentum causes them to impact and adhere to the fiber surface. Through diffusion, very small particles exhibit Brownian motion, moving randomly due to collisions with air molecules. This random movement increases their chances of contacting filter fibers. HEPA filters are most efficient at capturing both very small and large particles. Paradoxically, particles around 0.3 microns, the most penetrating particle size, or MPPS, are slightly harder to capture, yet HEPA filters still maintain 99.97% efficiency at this challenging size. The combined action of these three mechanisms makes HEPA filters remarkably effective, which is why they're essential components in all classes of biosafety cabinets. Biosafety cabinets rely on three fundamental airflow principles to provide protection. First, inward airflow prevents the escape of contaminants, protecting laboratory personnel. Second, downward laminar flow provides a sterile working environment, protecting samples from contamination. Third, filtered exhaust ensures that all air leaving the cabinet is clean, protecting the environment. Let's examine how airflow works within a biosafety cabinet. The first principle is inward airflow. Air flows from outside the cabinet through the front opening. This creates negative pressure inside the cabinet, preventing contaminated air from escaping and protecting personnel. The second principle is downward laminar flow. HEPA-filtered air flows down in parallel streams. This creates a sterile curtain of air that protects samples from contamination. The parallel airflow prevents turbulence that could mix clean and contaminated air. The third principle is filtered exhaust. All air inside the cabinet, which may contain hazardous particles, passes through HEPA filters. These filters remove 99.97% of particles, zero point 0.3 microns or larger, ensuring that only clean air is released to the environment. When all three airflow principles work together, they create a complete protection system. Inward airflow protects personnel, downward laminar flow protects samples, and filtered exhaust protects the environment. These airflow principles apply differently across biosafety cabinet classes. Understanding these fundamental airflow principles is essential for proper biosafety cabinet selection and safe operation. Class 1 biosafety cabinets are the most basic type of BSCs available in laboratories today. Their basic design consists of a work area with an open front, similar to a chemical fume hood, but with one critical difference. All exhaust air passes through a HEPA filter. Class 1 cabinets operate with a principle of inward airflow. Room air is drawn in through the front opening at a minimum velocity of 75 linear feet per minute. This contaminated air then flows upward inside the cabinet and through a HEPA filter, removing airborne contaminants before being exhausted from the cabinet. The key features of a Class 1 BSC include its simple design and its ability to provide protection for both personnel and the environment. Importantly, Class 1 cabinets provide protection for laboratory personnel and the environment, but they do not protect the research materials from contamination. This is because room air, which may contain contaminants, flows directly over the work surface and samples. Class 1 biosafety cabinets provide protection for the operator and environment, but not for the product or samples being handled. Air is drawn in through the front opening, providing a protective barrier between the work area and the operator. Class 1 BSCs are suitable for work with low to moderate risk biological materials, typically at biosafety levels 1 and 2. They are ideal for procedures where operator protection is the primary concern, as they provide a high level of personnel protection. Class 1 cabinets are also appropriate for handling toxic chemicals or radionuclides alongside biological materials. Common applications include basic microbiological procedures and sample preparations where sterility is not critical. However, Class 1 BSCs have significant limitations. Most importantly, they provide no protection for the product or samples from contamination. They present a high risk of cross-contamination between samples due to unfiltered air flowing directly over the work area. This makes them unsuitable for work with cell cultures, sterile media preparation, or any procedure requiring product protection. Compared to Class 2 cabinets, Class 1 BSCs have less controlled airflow patterns, which can impact their overall effectiveness. When deciding between a Class 1 and Class 2 BSC, consider the types of protection you need. Both provide operator and environmental protection. However, the critical difference is that Class 1 cabinets do not protect your samples or materials from contamination, while Class 2 cabinets do provide product protection. In summary, choose Class 1 BSCs when product protection is not needed and when operator and environmental protection are your primary concerns. Class 2 biosafety cabinets are the most commonly used type in laboratory settings worldwide. These cabinets feature a partially open front design with an inward airflow to protect personnel. A key feature of Class 2 cabinets is the HEPA-filtered downward laminar flow system. The airflow system creates multiple layers of protection. The inward airflow protects personnel from exposure to potentially hazardous materials. HEPA-filtered downward laminar airflow protects the product from contamination. Finally, the exhaust system with HEPA filtration protects the environment from aerosols and particulates generated inside the cabinet. Class 2 biosafety cabinets are utilized in approximately 95% of laboratory applications requiring containment. Class 2 biosafety cabinets come in several subtypes, each with different specifications designed for various laboratory applications. These subtypes include A1, A2, B1, and B2, which differ in airflow patterns, percentage of air recirculated, and exhaust requirements. Selecting the appropriate Class 2 BSC subtype depends on the level of hazard, whether volatile chemicals will be used, and facility constraints. The Class 2 Type A1 biosafety cabinet is designed for working with low to moderate risk biological agents. It features a front opening for user access and a work surface where procedures are conducted. HEPA filters are key components, with a supply filter that protects the work surface and an exhaust filter that cleans air before it's released. The Class 2 Type A1 cabinet maintains a minimum inflow velocity of 75 feet per minute at the front opening. Clean, HEPA-filtered air flows down from the top of the cabinet onto the work surface. A key characteristic of Type A1 cabinets is that 70% of the air is recirculated through the supply HEPA filter. The remaining 30% is exhausted through the exhaust HEPA filter, which may be recirculated into the laboratory. Let's examine the technical specifications of Class 2 Type A1 cabinets. Class 2 Type A1 cabinets are suitable for work with agents requiring biosafety level 1, 2, or 3 containment. However, they have limitations. They're not suitable for work with toxic chemicals or radionuclides, and there's potential for cabinet contamination due to the recirculated exhaust. It's worth noting that Class 2 Type A1 cabinets manufactured before 2010 were formerly designated simply as Type A. Class 2 Type A2 biosafety cabinets feature significant improvements over the A1 models. They operate with an increased inflow velocity of 100 feet per minute, providing better containment of potentially hazardous materials. The A2 model features a sealed design with a negative pressure plenum surrounding contaminated positive pressure plenum areas. Unlike the A1 models, Type A2 cabinets can be used with minute amounts of volatile toxic chemicals and trace amounts of radionuclides. Class 2 Type A2 biosafety cabinets are currently the most common type found in research laboratories worldwide. Their popularity stems from their versatility, enhanced safety features, wide commercial availability, and balance of containment with ease of use. To summarize, Class 2 Type A2 biosafety cabinets feature 100 feet per minute inflow velocity, a sealed design with negative pressure plenums, compatibility with small amounts of chemicals and radionuclides, and the option for thimble-connected exhaust systems. These features make the A2 cabinet the standard choice for most laboratory applications requiring both product and personnel protection. Class 2 Type B1 biosafety cabinets have distinctive features that set them apart from other BSC types. The cabinet includes a work surface, front opening, HEPA filters, and a dedicated exhaust system. Class 2 Type B1 cabinets maintain an inflow velocity of 100 feet per minute, providing personnel protection. A key feature of Type B1 cabinets is the air distribution. 30% of the air is recirculated through the cabinet to provide product protection. The remaining 70% of air is exhausted through dedicated ductwork, which helps remove volatile compounds from the work area. Let's summarize the key features of Class 2 Type B1 biosafety cabinets. Class 2 Type B1 cabinets are suitable for specific laboratory applications. They can be used with minute amounts of volatile toxic chemicals and trace amounts of radionuclides, while providing protection for biological materials. There are important requirements for operating Class 2 Type B1 cabinets. These cabinets must be connected to an external exhaust system through dedicated ductwork. Without a properly functioning exhaust system, the cabinet will not provide adequate protection. Class 2 Type B2 biosafety cabinets are also known as total exhaust cabinets. Unlike other Class 2 cabinets, these specialized units exhaust 100% of the air to the outside with no recirculation. The defining feature of B2 cabinets is their airflow pattern. Room air enters through the front opening and from the sides. All air, both room air and supply air, passes through HEPA filters before being exhausted outside. No air is recirculated back into the cabinet or the laboratory. Class 2B2 cabinets are specially designed for work involving volatile toxic chemicals and radionuclides. Their total exhaust design safely removes chemical vapors and fumes that would otherwise recirculate in other cabinet types, potentially damaging filters or re-entering the laboratory. While B2 cabinets offer superior protection for certain applications, they come with significant requirements. They consume substantially more energy than other BSC types and must be hard ducted to a dedicated building exhaust system with sufficient capacity. Installation requires careful integration with the building's mechanical systems. The exhaust system must have fail-safes to ensure continuous operation even if the primary exhaust fan fails. These requirements significantly increase both installation and operating costs compared to other biosafety cabinet types. Due to their specialized nature and high operational requirements, Class 2B2 cabinets should only be selected when absolutely necessary for work involving volatile toxic chemicals or radionuclides that cannot be safely handled in other cabinet types. For most biological work, even with small amounts of chemicals, a Class 2A2 cabinet with a canopy connection may be sufficient and more energy efficient. Class 3 biosafety cabinets represent the highest level of containment and protection available. These cabinets are completely enclosed, gas-tight systems that are operated through attached rubber gloves integrated into the cabinet walls. Class 3 BSCs provide the highest level of personnel and environmental protection. Let's examine their key features. Class 3 BSCs use HEPA-filtered supply air to maintain a pathogen-free working environment. The exhaust air is also HEPA-filtered, providing a crucial second layer of protection to prevent any release of dangerous pathogens. Class 3 biosafety cabinets are primarily used in facilities requiring Biosafety Level 4 containment. They are designed for work with the highest risk pathogens, including deadly viruses that can spread through aerosols and have no available treatments or vaccines. In the biosafety level containment hierarchy, Class 3 cabinets are required for the highest risk work at BSL 4 and may also be used at BSL 3 for certain pathogens. Class 3 cabinets feature specialized transfer systems to safely move materials in and out of the cabinet without breaking containment. To summarize, Class 3 biosafety cabinets provide maximum containment and protection through their fully enclosed design, specialized access systems, and HEPA filtration of both supply and exhaust air. These cabinets represent the highest level of containment available, making them essential for work with the most dangerous pathogens in maximum containment laboratories. When selecting a biosafety cabinet, several critical factors must be considered to ensure appropriate protection and functionality. There are four main factors to consider: risk assessment, type of protection needed, agents and chemicals used, and laboratory space constraints. Risk assessment is the foundation of BSC selection. The biosafety level of your work dictates which cabinet class is appropriate. For BSL 1, a Class 1 or 2 BSC may be optional. BSL 2 work typically requires a Class 2 BSC, while BSL 3 requires Class 2 or 3 cabinets. BSL 4 work demands Class 3 BSCs or Class 2 with additional protective measures. The type of protection you need is critical in selecting the appropriate cabinet. All BSC classes provide personnel and environmental protection, but product protection is only offered by Class 2 and Class 3 cabinets. The types of agents and chemicals you work with significantly impact your BSC selection. For biological agents only, any Class 2 BSC is suitable. However, when working with volatile chemicals, you'll need a Class 2 B1 or B2 cabinet with external exhaust. For highly toxic chemicals, Class 2 B2 or Class 3 BSCs are required. Laboratory space constraints are often overlooked but critical in BSC selection. Consider the physical dimensions, ventilation requirements, utility connections, and certification access needs for your chosen cabinet. The final and perhaps most important step in selecting a BSC is to consult with biosafety professionals. Expert consultation ensures compliance with requirements, proper integration with facility ventilation, addressing unique research needs, and planning for future adaptability. To summarize the BSC selection process, follow these 5 key steps. Assess risk level, determine protection needs, evaluate agent and chemical requirements, consider space constraints, and consult with biosafety professionals. Proper placement of biosafety cabinets in the laboratory is critical for both safety and functionality. Let's examine a typical laboratory layout to identify critical considerations for BSC placement. First, let's look at a poor BSC placement. This location near a door is problematic due to air disturbances from foot traffic. Traffic flow around doors creates air currents that can disrupt the protective airflow patterns of a BSC. A better placement is away from doors, windows, and air vents, preferably in a low-traffic area of the laboratory. Proper clearance is essential. Maintain at least 30 centimeters from the ceiling and 15 centimeters from walls to ensure adequate airflow around the cabinet. Let's summarize the critical factors to consider for proper BSC placement. It's important to note that air turbulence from nearby equipment or personnel movement can compromise the protective capabilities of a biosafety cabinet. Ergonomics are crucial for laboratory safety and productivity. The BSC should be positioned at a comfortable working height, typically 75 to 80 centimeters. Workflow considerations are equally important. The BSC should be positioned to optimize material flow, provide sufficient space for equipment, and allow easy access to other laboratory areas. Before finalizing BSC placement, consult with certification professionals, verify that the placement meets facility requirements, and check that electrical and plumbing needs can be accommodated. As a best practice, document your BSC placement decision process for future reference and to facilitate certification. Personal protective equipment remains essential when working with biosafety cabinets. 3 key PPE items are required: laboratory coats, gloves, and eye protection. Laboratory coats should have a fully buttoned front and long sleeves with fitted cuffs to provide adequate protection. For higher biosafety levels, disposable coats may be preferred. Always wear your lab coat closed while in the laboratory. For biosafety level 1 and 2 work, single gloves are typically sufficient. For BSL-3 activities, double gloving is recommended. Gloves should extend over the cuffs of your lab coat to prevent skin exposure. Change gloves whenever they become contaminated or compromised, and remove them carefully to avoid spreading contamination. Eye protection includes safety glasses with side shields, goggles for splash protection, or face shields for additional protection. Remember that eye protection is required even when the biosafety cabinet sash acts as a barrier. Let's address some common misconceptions. First, BSCs do not eliminate the need for PPE. Second, gloves are always necessary when working in a BSC. And third, eye protection is not redundant even with the cabinet sash in place. PPE remains essential when using biosafety cabinets because BSCs primarily protect samples and the environment, not just personnel. Spills and aerosols can still contact exposed skin during work. If mechanical failures occur, PPE provides a critical backup layer of protection. Additionally, PPE prevents contamination when placing hands and arms into the cabinet or removing them. To summarize best practices, always wear complete PPE before approaching a biosafety cabinet. Check PPE integrity before each use. Remove PPE properly after completing your work, and never reuse disposable PPE items. Proper cleaning and disinfection protocols are critical for maintaining biosafety cabinet function and preventing contamination. Daily cleaning procedures should be performed both before and after using a biosafety cabinet. Before using a biosafety cabinet, turn it on and allow it to run for at least 5 minutes. Then wipe all surfaces with 70% ethanol or isopropyl alcohol. Always allow the disinfectant to air dry completely and document the cleaning in your logbook. After use, remove all materials and waste from the cabinet. Wipe all surfaces working from top to bottom to avoid recontamination. Disinfect with an appropriate agent for your specific contaminants and let the cabinet run for at least 10 minutes before turning it off. Selecting the appropriate disinfectant is crucial for effective decontamination. Different agents are effective against different types of contaminants. 70% ethanol or isopropyl alcohol is effective against most bacteria, fungi, and some viruses, with a contact time of at least 1 minute. It evaporates quickly and is non-corrosive to cabinet surfaces. 10% bleach solution provides broad-spectrum disinfection, including bacterial spores, but requires 5 to 10 minutes of contact time. Be aware that bleach is corrosive and can damage cabinet components. Quaternary ammonium compounds are effective against bacteria and enveloped viruses with a 10-minute contact time, but may leave residues and are less effective against spores. Regardless of the disinfectant used, adequate contact time is essential for effectiveness. Many users prematurely wipe surfaces dry, reducing disinfection efficacy. Using proper cleaning techniques is essential to maintain cabinet function and prevent cross-contamination. Always clean from top to bottom to prevent recontamination of cleaned surfaces. Use lint-free wipes to avoid particle generation and allow proper contact time for disinfectants. Dispose of used wipes as biohazardous waste and clean carefully around HEPA filters without touching them directly. Never use abrasive cleaners that can damage surfaces and avoid spraying disinfectants directly onto surfaces as this can cause aerosolization. Avoid soaking electrical components, mixing incompatible chemicals like bleach and ammonia, and never touch HEPA filters with cleaning wipes. Regular deep cleaning schedules are critical for maintaining biosafety cabinet performance beyond daily disinfection procedures. Daily cleaning involves surface disinfection of the work area by lab staff. Weekly cleaning should include all interior surfaces, including sides and back panels. Monthly procedures should include removing the work surface to clean the sump below, typically performed by the lab manager. Annual deep cleaning coincides with certification and should be done by a certified technician. All cleaning activities must be documented in a logbook, including the date, personnel performing the cleaning, and the specific procedures completed. To summarize key cleaning protocols for biosafety cabinets: clean surfaces both before and after each use. Match your disinfectant to potential contaminants in your work. Ensure adequate contact time, typically 1 to 10 minutes depending on the disinfectant. Always clean from top to bottom using correct techniques to prevent recontamination. Follow a regular deep cleaning schedule beyond daily procedures and maintain complete documentation of all cleaning activities. Managing spills inside biosafety cabinets requires specific procedures to maintain safety and containment. The main principles of spill management include keeping the cabinet running at all times, containing the spill immediately, decontaminating thoroughly, documenting the incident, and following specific protocols based on the type of spill. If a spill occurs, immediate actions are critical. First and most importantly, do not turn off the BSC. The cabinet's airflow helps contain the contamination. Alert nearby personnel about the incident. Quickly assess the size and type of spill. If your PPE is contaminated, remove it carefully following proper procedures. Then apply the appropriate disinfectant according to your lab's protocols. Keeping the BSC running is critical, as the continuous airflow helps prevent contaminants from escaping. The cabinet's inward and upward airflow directs aerosols away from the user and into the HEPA filters. Different types of spills require specific approaches. For biological spills, use your lab-approved disinfectant, cover with absorbent material, allow sufficient contact time, and dispose as biohazardous waste. For chemical spills, use the appropriate chemical-specific neutralizer and spill kit, assess ventilation requirements, and dispose as chemical waste according to regulations. Using the proper absorbent material is crucial for effective spill management. Paper towels are suitable for small liquid spills, while absorbent pads are better for larger spills. Solidifying agents can help contain hazardous liquids, and specialized neutralizing materials should be used for chemical spills. When using absorbent materials, work from the outside of the spill toward the center to prevent spreading contamination. Allow sufficient contact time according to your disinfectant specifications. Proper documentation of spill incidents is essential. Your documentation should include the date and time of the incident, type and volume of spilled material, decontamination procedures used, PPE and materials used for cleanup, names of personnel involved, corrective actions taken, and supervisor notification details. There are situations when you should seek additional assistance. These include large spills greater than 500 milliliters, incidents involving highly hazardous materials, spills extending outside the BSC, compromised BSC operation, or any exposure to personnel. In these situations, immediately contact your biosafety officer, laboratory supervisor, or emergency response team according to your facility's procedures. To summarize the key points about managing spills in BSCs, always keep the BSC running during spill response. Use appropriate materials specific to the spill type. Follow your laboratory's standard operating procedures. Document all incidents thoroughly and know when to seek additional assistance. Biosafety cabinet decontamination differs significantly from routine disinfection. Full decontamination aims to completely eliminate all microorganisms from all BSC surfaces, including HEPA filters, while routine disinfection only addresses accessible work surfaces. Full decontamination of a biosafety cabinet is necessary in several specific situations. These include before HEPA filter changes, before relocating the cabinet, prior to major maintenance procedures, after significant biohazardous spills, when changing research with different risk groups, and per institutional or regulatory requirements. There are 4 primary methods used for complete BSC decontamination: formaldehyde gas, chlorine dioxide, hydrogen peroxide vapor, and ultraviolet light, which has significant limitations. Formaldehyde gas has been the traditional decontamination method for decades. The process involves heating paraformaldehyde to produce gas under specific humidity conditions, followed by a 6 to 12-hour contact period. While highly effective against all microorganisms, formaldehyde is a known carcinogen and serious health hazard. Due to these risks, it's being phased out in many institutions. Chlorine dioxide is an increasingly popular alternative to formaldehyde. It's generated from sodium chlorite solution and distributed as a gas throughout the cabinet. The process requires only 1 to 3 hours contact time, significantly less than formaldehyde. While chlorine dioxide is less toxic and more efficient, it's still corrosive to some materials and requires careful handling. Hydrogen peroxide vapor is becoming the preferred method in many facilities. The process involves vaporizing hydrogen peroxide solution and distributing it throughout the cabinet. It requires only 30 to 90 minutes contact time and decomposes into harmless water and oxygen. While highly effective and environmentally friendly, this method requires specialized equipment and has higher upfront costs. Ultraviolet light is sometimes used but has significant limitations. UVC light at 254 nanometers can damage microbial DNA, but only works on directly exposed surfaces. It cannot reach shadowed areas, has no penetration of HEPA filters, and its efficacy is affected by distance, dust, and bulb age. UV light should never be considered a complete decontamination method, but only supplemental to proper chemical disinfection. Let's compare these decontamination methods. Formaldehyde gas has high effectiveness, but requires 6 to 12 hours and poses significant safety concerns. Chlorine dioxide is similarly effective, but with reduced time and medium safety concerns. Hydrogen peroxide vapor offers high effectiveness with the shortest contact time and lowest safety concerns. UV light has limited effectiveness, variable time requirements, and while safe to use, is only suitable as a supplemental method. Regardless of the method used, proper validation and documentation are essential. Biological indicators, typically Geobacillus styrothermophilus spores, are required to verify efficacy. Documentation must include the method used and parameters, date and technician identification, biological indicator results, and certification after decontamination is complete. Biosafety cabinets can experience several operational problems that may compromise safety and experimental results. Airflow alarms are one of the most common BSC problems. These alarms activate when airflow parameters fall outside acceptable ranges. When airflow is disrupted, the cabinet's protection capabilities are compromised. This triggers an alarm to alert users of the unsafe condition. Users can troubleshoot certain airflow issues. First, check for obstacles near exhaust areas and verify the sash is positioned correctly. Ensure the power supply is stable. If the alarm persists after these checks, contact maintenance personnel, as this may indicate a more serious issue with the cabinet. Sample contamination is a serious problem that can compromise research results and potentially create safety hazards. Contamination often occurs due to poor aseptic technique, improper work area setup, cross-contamination between samples, or inadequate disinfection practices. To prevent contamination, follow proper hand movements inside the cabinet, working from clean to dirty areas. Always thoroughly disinfect the work surface before and after use. Minimize traffic around the BSC during operation, as air disturbances can disrupt the protective airflow patterns and introduce contaminants. Improper sash height is a common user error that can significantly impact BSC performance and safety. When the sash is positioned too high, containment is compromised, reducing protection for both the user and samples. If positioned too low, it alters airflow patterns and may restrict workspace accessibility, potentially triggering alarms. Always use the indicated height markers and certified operating position for your specific cabinet model. Never disable sash alarms. When accessing the cabinet, return the sash to its proper operating height immediately after completing your task. Blocked grills are one of the most common user-related operational problems with BSCs. Items such as towels or papers covering the front grill can disrupt the inflow of air, compromising containment. Similarly, equipment or storage containers positioned over the back grill can block downflow, creating turbulence and potential contamination zones. To resolve grill blockage issues, always keep grills completely clear and use stands to elevate equipment when necessary. Position all items at least 4 inches away from grills. This problem is entirely user resolvable and requires no maintenance personnel. Equipment malfunctions can range from simple issues that users can resolve to complex problems requiring technical expertise. It's important to distinguish between issues that users can safely address and those requiring certified maintenance personnel. Users can check power connections, verify circuit breakers haven't tripped, replace BSC light bulbs, and perform basic control system resets. However, contact maintenance immediately for motor or fan failures, electrical system faults, control board issues, unusual noises, or repeated alarm triggers. When troubleshooting BSC problems, it's crucial to quickly determine whether you can resolve the issue or if you need to contact maintenance personnel. Users can typically resolve issues related to blocked grills, improper sash height, simple power problems, and work practices. However, persistent alarms, mechanical failures, ongoing airflow issues, and filter problems require certified maintenance personnel to diagnose and repair. Remember, when in doubt about a BSC operational problem, it's always better to contact maintenance rather than risk compromising safety or damaging the equipment. One of the most dangerous misconceptions is that biosafety cabinets can be used like chemical fume hoods. Biosafety cabinets are specifically designed to protect users from biological agents. They use HEPA filters that trap microorganisms, but cannot filter chemical vapors. In contrast, chemical fume hoods are designed to protect against chemical vapors and continuously exhaust air outside of the building. Using volatile chemicals in most BSCs can damage the HEPA filters, contaminate the cabinet, and expose users to harmful vapors. Another common misconception is that all biosafety cabinets provide the same level of protection. In reality, different BSC classes and types offer varying levels of protection for personnel, products, and the environment. Class 1 cabinets provide good personnel and environmental protection, but no product protection. Class 2 cabinets offer different levels of protection based on their specific type. Class 2 Type B cabinets and Class 3 cabinets provide enhanced protection, especially when working with particularly hazardous agents or when chemical protection is needed. A widespread misconception is that UV lights in biosafety cabinets provide complete sterilization. While UV lights can help reduce microbial contamination, they have significant limitations. UV light cannot reach shadowed areas, diminishes in effectiveness over time, and requires specific exposure times to be effective. Additionally, UV light is not effective on all surfaces and should never replace proper chemical disinfection protocols. Perhaps the most dangerous misconception is that biosafety cabinets automatically provide protection regardless of how they are used. Proper BSC use is essential for effective protection. This includes allowing the airflow to stabilize before beginning work, working at least 4 inches inside the cabinet, and using slow, deliberate movements. Improper practices dramatically reduce protection. Common errors include starting work immediately after turning on the BSC, working at the very edge of the workspace, making rapid arm movements, and blocking air grills. The final critical misconception is that biosafety cabinets protect against all laboratory hazards. BSCs are specifically designed to protect against aerosols, biological agents, cross-contamination, and most microorganisms. However, standard BSCs do not protect against most volatile chemicals, radiological hazards, physical injuries, or heat and fire. It's worth noting that some specialized cabinets like Class 2 Type B2 and certain Class 3 BSCs can handle limited chemical work, but this is not true for most BSCs found in laboratories. Biosafety cabinet technology continues to evolve with several promising developments on the horizon. Energy efficiency is a major focus in new BSC designs. Manufacturers are developing cabinets with DC motors, smart airflow controls, and eco-friendly refrigerants. Integration with laboratory information management systems allows BSCs to automatically record operating parameters and user information, enhancing compliance documentation. Remote monitoring through IoT sensors gives laboratory managers real-time alerts about cabinet performance and potential issues, even when they're away from the lab. Enhanced ergonomic features include adjustable working heights, improved lighting, and reduced noise levels, addressing user comfort during extended work periods. These technological advances are creating smarter biosafety cabinets while maintaining core protection principles. Next-generation BSCs offer multiple benefits, including reduced environmental impact, lower operating costs, improved compliance tracking, enhanced user comfort, and predictive maintenance. As laboratories become more digitized, these smart BSC features will become increasingly important for efficient operations while maintaining the highest safety standards.